Welcome to Happy Path Programming. I'm Bruce Eckel.
I'm James Ward.
Good morning.
Morning. It's good to be back.
It is.
We are vaccinated and healthy and
well, getting there anyway.
That's right. On the journey.
Yeah. Yep. It's liberating.
Yes.
It feels liberating, especially since the first day in both cases for me was pretty tough.
Yeah.
But I'd much rather have that than go through the actual virus again.
Yeah.
That was way worse.
Way worse.
Yeah.
And we should say it again in case people missed on the last episode that we're going to do an in-person conference up here in Crested Butte this summer, right? August.
We are. Yeah.
August 15th or something.
Yes. It's around then, it'll be on, I'll set up the whole websites and everything. I realized STFU,
the Summer Tech Forum
Unconference.
Yeah.
Yes, that was suggested by several people on the various news groups and Slack channels and stuff.
Maybe next winter we'll have WTF again, and then
maybe. Yeah. I mean, because a lot of people haven't been out here in the summer, and so they don't know how amazing it is.
Yeah,
and I imagine once people come, they'll go, oh, we definitely need to have I'd love to do more
in winter.
I really enjoy these things. This is something that gives me a lot more energy than it takes. So those are things that I like to do. The one thing I realized after getting the reservation at the hall where we hold it was, oh wait, in the summer we have often monsoon season when it rains in the afternoon and is clear in the morning.
It changes our schedule from in the wintertime we do sessions in the morning and play in the afternoon.
Right.
In the summertime, got to flip it.
Right. So I have a request in to change that, but that's the only thing that might change the dates, but I think it's still okay.
Yeah.
So anyway, that's a lot of people looking forward to that. I think there's a hunger for, and the rate that vaccinations are happening,
that will be to wear masks.
That will be a request, is that people be vaccinated.
Yeah.
To come, but that shouldn't be unreasonable.
Yeah. By then, I think our whole county is going to be basically vaccinated in the next month. So
right, which is important because a lot of tourists come through here, so there's a lot of potential exposure.
Yeah. So you've been thinking about build tools again.
I've been stuck in build tools. Well, in particular
for 20 years now.
Most of those I've been able to deal with. I mean, usually the build tools with the books, I write a program that will automatically generate the configuration. So it's not so hard to understand that I can do that. But I started thinking about things that you don't want to do when you're designing a build tool. And there are things like, I think we've agreed that ultimately a build tool needs to have a programming language behind it of some kind.
And you should probably invent one for that purpose would be a good idea, right?
I don't think so. I think you're being sarcastic. Okay.
But people do.
Oh, of course they do. And then they discover that, oh no, this is way harder than I thought. And now I'm doing a language instead of a build tool. Yeah. I mean, I saw that happen with Make.
Yeah.
Because you just go, they just kept adding features
until they
go.
Slope.
It is a slippery slope.
Yeah.
And so, use an existing language. But I think one of the problems with Gradle and using Groovy is that here you got Java programmers and Gradle says, hey, Groovy, it's like Java, but it isn't. It's like, it sort of looks like Java, but it has so many different, so you have to learn this.
I mean, I can understand the draw when Han started creating Gradle to use Groovy because he wanted something that had a build DSL, something that provided a nice kind of declarative syntax with some, using Java, I think would have been a bad idea.
Oh, really?
Yeah.
See, because I feel like
it would look terrible. Like your build definition would be just hideous.
Yeah, but you'd understand it. You wouldn't be learning a new language.
Yeah.
I would say, my approach would be, if you're creating a build tool for Java programmers, either use Java or use something so different.
XML, let's say.
Well, that's not a language, but I mean, use something like Python.
Yeah.
It's like, so it's very clearly not Java.
Yeah.
Whereas Groovy is kind of like, oh yeah, it's a lot like Java, except when you try and do Java things with it, no, it's different.
Yeah.
So it confuses you.
Yeah.
And the other thing is, I don't think I would use. I don't think the value of the DSLs that they use, where you have the configuration. There was a lot of things they did, I think, just to save. Oh, let's see if we can cram this into smaller and smaller things. And now we've got it. So all you do is import a plugin, and all this magic happens. It's like, do you want all? If you do too much magic, it just becomes a weird black box.
Yeah.
And I don't find
it requires a magician to understand it.
Yeah, I think I don't think the DSL actually creates enough value for the confusion that it introduces to me. I think I'd rather just do function calls and say, configure this using this function call, configure that. It'd just be less mental hoops to jump through.
Yeah, in some ways, I appreciate the Maven model of when you're in the declarative world of XML, which is where most people spend most of their time. It's so significantly limited in what you could do that it does make it more easily understandable.
Mm-hmm.
And then if you do need more power, you drop down to Java and you write additional stuff in Java.
Mm-hmm.
In some ways, I appreciate that model because at least it's clear.
Mm-hmm.
It's not fun when you have to go into the Java side of things. To write a Maven plugin,
because I'm sure there's some sort of complex API that requires a lot of study to understand.
It just is. It opens up a can of worms that's not very fun to deal with.
Mm-hmm.
The API is actually not too bad.
Yeah,
but I still think that SBT is one of the better models for a build tool. Because it's immutable, it's Scala, so you have an actual general purpose
You're
language.
programming in Scala, your SBT is in Scala. See, that's my point.
Yeah.
So do it that way, or just do it with a language which is designed to be simple.
Yeah. Yeah, I think I would really love to explore one of these build tools that uses DAL, the DAL language as
how do you spell that?
DHALL. It's like the Indian dish.
I think that's DAHL.
Maybe.
I think DAL. It's the same spelling as the lentil soup.
I think so, but maybe I'm wrong about that.
Well, anyway,
I'm pretty sure the language is DHALL.
Okay.
But I would love to explore the idea that you should have a language that is not general purpose.
Mm-hmm.
Statically typed,
mm-hmm.
functional, and it may be harder to learn for somebody who's not a DAL developer, but I think that there are sufficient constraints on the languge that the learning curve is potentially not that bad. But there's a couple of build tools that use DAL, so I need to give them a try. One was for like C or C++, and I can't remember what the other one was for, but yeah, I think that, like the episode where we talked about how serialization on the surface seems like this simple problem, and then it turns out that many decades later we're still trying to solve the serialization problem, and it turns out that it is not a simple problem. I think build tools are in the same bucket, where it's like, gosh, why do all build tools suck? And it's like, well, maybe the problem that we're solving is actually really hard. But then also I think that maybe we also haven't necessarily uncovered the right foundational pieces that need to be there.
Right. Well, mental model kind of things
that
we're talking about.
Like SBT, the fact that the build definition is immutable, it's really hard to use a build tool that doesn't use that paradigm for me.
So when you say immutable, well, for example, like Gradle has life cycle things.
Yeah.
And I'm guessing that it's like
there's some magic state machine,
right.
And when mutations get applied to the build configuration, happens at some seemingly random point in execution,
unless you know the deep underlying details, in which case you know when it happens.
Yeah, just that life cycle there is a life cycle. There is a state that is things happen, things change, other things happen. It just is very confusing and very hard to debug. Whereas with SBT, you can go into SBT and be like, what is the value of this thing? And SBT will tell you exactly what the value of that thing is.
Okay, so based on that, I would say that things like maybe make files and ant files would be immutable. Because I don't think there's anything that changes.
I think that in the case of, maybe because it's really just this like flat procedural thing. Maybe it is more immutable. SBT though will actually, it does the whole like directed acrylic graph stuff that Gradle does to manage dependencies and run things in parallel and all that. Like that all happens, but the model for how you define the build configuration is immutable. And
so you don't have to know that
when something changed, why it changed, dig into the source code for why this thing changed.
Right.
Yeah.
So does it do it right at the beginning? It creates the directed acyclic graph?
SBT, yeah.
Okay.
Yeah. So when you load the build and it parses all the configuration and gets to the state of the build, then that's your state that it's going to run,
and it stays the same forever.
Yeah. There are a few caveats to that, which remember when we were working on our Scala 3 book build stuff, you can do a dynamic task, which kind of gets around some of that. So there are a few ways to circumvent the normal behavior, but the normal behavior of SBT is, it essentially parses the build configuration or runs the build configuration, gets to a state, and then runs tasks against that state.
Okay. Well, yeah.
So I think that's one of the things that build tools should do is future build tools should have a immutable configuration model. That's been super helpful, especially for debugging, because I think with any build tool, you have to debug your build, and debugging a Gradle build is no fun at all.
I don't even know what the process is.
My strategy is printlns. Just add printlns, print things out. But then that gets hard because as the time that I'm printing this thing is at the right time because it's not immutable. And so I can print something and then later the value can be changed, and then the value that I'm seeing is not the value that's actually being used when it runs the task. And
when you put it that way, it sounds very difficult.
Yeah. No, it's not fun to debug Gradle builds.
Yeah.
Yeah. So I don't know. Matt Rabel tweeted yesterday. He's like, which build tool will you use on a future project, Maven or Gradle? And I was like, man, I wish there was a good third option. And there's just not yet a good third option.
Yeah. So we're still befuddled about build tools. Maybe, somebody needs to do a PhD dissertation or whatever on build tools, or we need a language designer to look at it. Somebody who's, just has a bigger brain than ours.
Yeah.
But is also
Hans
compassionate.
Has a much bigger brain than ours.
Who does?
Hans.
Oh yeah. Yeah. He can keep all that stuff in his head, but
yeah.
But also with compassion for the end user, to be able to say, what mental model does the end user need?
Yeah.
Not what mental model, not that it's a directed acyclic graph of dependencies. That doesn't help me figure out how to solve my problem.
Yeah. I can understand on the build designer side.
Sure.
the things you need to think about are caching, configuring, reading, writing files, all that kind of stuff. The user doesn't care about. I mean, obviously they care that things are cached and are fast, but
that's not the problem they're trying to solve.
Exactly. Yeah. And maybe that's one of the problems with build tools, is that build tools are written with different goals in mind than the end user, than the users of those build tools have.
Yeah, and I think maybe what's necessary is to say, oh, we have more than one mental model here. We have the mental model of the constructor of the build tool, and then we have the mental model of the end user. And I think when you don't, if you don't keep that in mind, you end up with something that the end user looks at and goes, I don't know where to start, what to do. I have all these options. I don't even know what all the options are. I don't know what I can ask for.
Yeah.
Any of those things. So,
yeah.
Mm.
Yeah. One reason why I continue to use Gradle usually on new projects is the continuous mode, where it continuously like recompiles, reruns stuff. Quarkus, the Quarkus framework, has that for Maven, and it's done really well. Quarkus has done a lot to create a really nice developer experience, and you can use Maven or Gradle, but their Maven support has that continuous mode, which is awesome. But because I mostly use Kotlin, and Quarkus does not yet support Kotlin coroutines, so I'm like, I want to use Quarkus, but until there's Kotlin coroutine support, I just can't really use it for anything real. I've built little hello world things with it, but for anything real, it's like if I'm in Kotlin, I'm going to use coroutines. I know they're working on coroutine support in Quarkus, but
so we came across a topic. I don't know, last time or the time before, I think, when you brought up
Reactive.
Reactive.
One, yeah.
And I feel like that was one of those things where I just kind of said, this is a new thing. It's kind of heavily biased towards I don't know, stuff I'm not interested in right now. Anyway, I skipped it all. So
yeah.
What's the deal? What's the mental model for Reactive?
Yeah. It's weird because with Reactive, really what the problem that it's solving is efficiency for the machine. Because Reactive is so there's the Reactive manifesto, which the TypeSafe Lightbend folks came up with a long time ago.
Is that while you were there?
Oh. Yeah, I worked with Jonas Bonner and Victor Klang and Roland on that. It was mostly they're the Akka folks, and so a lot of it was written from kind of their perspective. And what I've since realized is that there's kind of like two different sides of Reactive. There's the Akka side is about trying. It kind of takes the mental model of Erlang, where it's like, all right, we have a hierarchy of things that communicate, and we need to be able to handle that communication in a way that is efficient, but is also able to recover from when things go wrong. And this is like the actor supervision model. So that's where the Reactive manifesto really comes out of, is trying to categorize that stuff. And there's I'm not going to remember off the top of my head the 4 categories of the Reactive the Reactive manifesto, but there's another side of Reactive which has been more on the side that I've focused more of my energy on, which is really just non-blocking IO. And non-blocking IO, the whole reason for it is just because it's more efficient to be non-blocking. So this is going to get in the weeds for a bit, and then hopefully you can help pull me out of the weeds. But what happens usually in a program is you are communicating from one thing to another thing, and that could be from your in-memory process to the file system or across the network, and those things take a long time to do that relative to what you're doing in process. And if your process is just sitting there waiting for that thing to complete, then it's wasting resources that it could otherwise be using for something else. And so the whole point of non-blocking reactive stuff is to allow the program to continue and go off and do other things. And then once that other thing completes, then you can resume execution of that thing. So it's really just an efficiency for the machine.
But everything that you said, I could put async in instead of reactive, and it would still be true.
Async doesn't necessarily mean that it's non-blocking, and I think that that's part of why the reactive term gained some usage over just saying async. So back in the weeds for a second, the way that, and my understanding of this is not like super awesome or deep, but the way that I understand the way that the actual like networking path on Linux and Windows works is that you've got this like network loop happening, and that it's looking to see, okay, do I have an 8K byte chunk in my buffer that I can then pass to the program, something like that. And so the you've got this loop happening on the network IO channel, and it's passing the data in. But you, on the program side, you if you're just waiting for a whole response to come back from like an HTTP request or a database request or whatever, like you want your program to be able to go off and do other things. And then that loop is happening on the network channel, accumulating some bytes and then accumulating them somewhere in some buffer. And then when the thing is fully completed, then resume the execution of your user code. And so, that's the non-blocking IO piece. Why that's different from async is you can be async without necessarily not being, you can be blocking on the IO channel and still have a program that is async. So usually when I talk about reactive, I combine async and non-blocking. So an example of this is that you can use the JDBC driver and in Java, which is the normal way to communicate to a database, and that IO is blocking. So what that means is that there's going to be a thread allocated to your database, JDBC database request from the time that you make the call to the time you get the response. There will be a thread allocated to that is mostly just sitting around waiting for the response to come back and for all the bytes to be there. And that is just a waste of a resource that could be used for something else. In the non-blocking world, you actually like fire off the request. You do have that non-blocking IO loop, usually Java NIO on the JVM, usually Netty, which is
are we talking like an event loop?
Uh-huh.
Yep. So it's going around saying, "Are you done? Are you done? Are you done?"
Yeah. Okay. As far as I understand it.
Okay.
And so there is that like loop. There is that, and I'm sure that there are
but it's
multiple
not a thread.
Threads. It's not a thread per request, essentially.
It's it's
got a thread pool.
In Python, you have an event loop which is doing that for its async.
Yeah.
And it's just one thing. It's not a bunch of threads. Okay.
Yeah. And so why this is different is in normal blocking code, your code is just going to execute top to bottom, and there isn't a way for the program to be able to deallocate its resources. And then when that event loop says, all right, I have something for you, then resume the execution and continue. There isn't a way to do that. And so that's why you have to be async. as well to be non-blocking. So you've got the event loop, which allows you to be non-blocking, but then your program has to have the ability to resume, execute, or to suspend and resume when the non-blocking loop tells you it has something for you. So you could be async. So you can actually like put async on top of JDBC, some blocking protocol, and make it async. But there's really not a lot of value to doing that unless it's actually non-blocking under the covers. And so what's happened is a lot of the HTTP clients, database clients, any network is an easy one, but a lot of those have switched over or they're evolved new protocols that are now actually non-blocking underneath the covers. The first generation of this was they would just slap async interfaces, wrap blocking calls into futures, completable futures, whatever. But it really wasn't value. There wasn't much value there until it was actually non-blocking as well.
So let me give you my current mental model for what async means.
Yeah.
So it's a trick. And that is, well, think about what's the normal thing, synchronous calls. So you call a function and it's synchronous because you wait until the function completes and then you go on.
Yeah.
That's a synchronous call.
Yeah.
What is an asynchronous call? You call a function and it gets somewhere and it says, oh, I'm waiting on this. This thing's going to take a while. What I'd like to do is return control to the caller. And to do that, I have to put in something that allows me to suspend this function in the middle and, do it. It's like, well, one way you could do it, or ways we've done that before, is like, well, you could have callback hell, you could have all these. So what the async mechanism is something where you go, okay, well, we can stop this and return control to the caller. And now it's basically the same kind of thing that you would do with a thread. You go, oh, I'll fire off a thread here. Now I got this thing running, and then I got my main thing running. And at some point later, well, I don't know, how do we do that? We have some mechanism for coming back to that function.
That's right.
When it's ready.
Yeah.
Okay. But I don't see, to me, that's because otherwise the function would block. I'd call the function and would say, oh, I'm waiting to get, something from this website. So I'm going to just stop and wait. Now it's blocked. Async allows you to not block this function.
Right.
But I feel like you're maybe talking about something else when you say non-blocking.
Non-blocking, I'm talking mostly about non-blocking IO, because IO is a really good thing to be able to wrap async around.
Sure.
You can't really be non-blocking without having some form of doing async.
Yes.
But you can be async without being non-blocking. So
okay, that's the part I don't understand.
Okay. So let's take an example of this as sometimes in a program you want to have like a delay. You want to say, all right, I for some strange reason I'm going to call this function, and I in that function I want it to just wait 10 seconds to call me back. And so you can do that in both a blocking way and a non-blocking way.
Okay.
And when you wrap async around that, then that allows you as the caller to suspend and resume your execution until that delay is completed. In the world of Java, the way that you would implement a blocking delay is with thread.sleep, because when you do thread.sleep, your thread is still allocated, and the JVM will say, okay, yeah, I'm just gonna put this thread in a wait state, and then it's going to, after the number of specified milliseconds or whatever, it's going to resume. and the JVM does
and
that.
the function that is calling thread.sleep is just going to stop and not.
That's right. Yeah. Yeah. If you move into the non-blocking async world, then you can have a delay, and the way that Akka,
I mean, that just sounds like a bad design to me. Is that because it just seems like that was one of the many bad designs that they put into Java at the beginning.
Thread.sleep.
Yeah. Well, threads, all of the threads.
Yeah,
was a bad
well,
design.
they're working on changing that with project is it Loom or whatever.
Loom, I think, yeah.
Yeah, and going back to green threads or enabling an alternative, which is fiber model of underlying concurrency, whatever. So they are working on a new model for it.
Mm-hmm.
Threads they turned out to be really heavyweight, right? Like there's a lot of resources.
It's like 700 megabytes per thread or something like that, or K or anyway, there's a whole bunch of memory. There's a whole, I mean, again,
the default thread size is a few megabytes.
Or that's right. That, right. Yeah. But again, that just sounds like a bad design. It doesn't sound like a fundamental concept.
Yeah. Yeah. So async, where you can be non-blocking, async is necessary to be able to handle that.
Mm-hmm.
And
or it's a strategy, because I mean there's other ways to do that are worse, but
yeah, I mean Go has channels or something, which is similar.
Yeah.
And, there are many. You could use an actor model. There are many different strategies for how you handle essentially async, like
right. And then there's callback hell. Right.
Yeah, and there's monads. Mm-hmm. So yeah, there's a lot of different ways to handle reactive or async non-blocking in Kotlin coroutines. And my favorite recently is Scala Zio, which solves similar problems. And so what's happened is that we've realized that just this crazy waste of resources that was blocking IO. And so most modern stuff has said, all right, we're going to be non-blocking anywhere that we can. And that's database drivers, HTTP clients, all that kind of stuff.
Any place where you cross a boundary from one processor to another.
Yeah. Process. So the easiest places to be non-blocking are network IO and file IO.
Well, yeah, I guess. I mean, assuming that the file is being controlled by Anyway, go on.
So most modern stuff is now non-blocking. It just is obvious that we shouldn't just waste resources because our programming model forces us to. And so the programming model has now shifted, where now developers have to think about async, which creates a much harder programming model for how we deal with this, but it's required in order to take advantage of non-blocking. So there's a number of different ways that on the JVM that you can be non-blocking async. Many different libraries, many different approaches. In Scala, there's futures, there's Zio, there's cats, there's a number of other ones. In Kotlin, mostly people just use coroutines or the Flow API if you're doing stream-oriented non-blocking stuff.
And then, so the streams, do we call them streams in Java, or are they? No, they're anyway.
It's streams. Yeah.
Okay.
Yeah,
and that's a similar thing that's in Java 8.
Those are not reactive. Streams and non-blocking is a whole nother interesting thing. And this is where the same folks that created the Reactive Manifesto created the reactive streams specification. And now a lot of the JVM based stream libraries are based on the reactive streams specification, and that is reactive. Obviously, the name says it. And so there's a number of implementations of reactive streams, and then there's a bunch of higher level APIs for doing non-blocking stream oriented stuff. I've mostly used Akka streams, which is a nice reactive it's built on top of Akka, so it's actors, but you could also use RX Java is one option. There's another option that Quarkus uses by default that's based on Vertex. Tons and tons of different options for how you do this. And ultimately, what it's all about in terms of the non-blocking stuff is just being more efficient. Mm-hmm. Not wasting threads and resources when you don't need to, but it complicates the programming model significantly.
It's a leaky abstraction.
Well, it's just as necessary. Your normal program is written in this imperative style, and there's no way to be like, okay, here is where I can suspend and come back later. Kotlin coroutines is, one example where they built it into the programming model. And so you write something that seems imperative, and then the compiler, figures out like, okay, here's the point where I can now suspend execution and resume. And so Kotlin does a lot of stuff to make the programming model nicer for you. Or I use monads mostly for this kind of thing because it enables reactive chaining of stuff. Because I'm a monad guy.
I think the thing that confused me about this is that, like in Python's async, it's not, there isn't a blocking. It's like the non-blocking aspect is built in because, well, why wouldn't you? I mean, why would you have the blocking thing when you're doing some kind of async?
Yeah.
So the fact that you're telling me, and this is why I'm arguing, that sounds like a bad design if it blocks and you're trying to wrap it into any kind of a concurrency model.
Yeah. I think Ruby is interesting in this respect because they don't really have threads in Ruby. And so I'm sure this has changed, but at one point you couldn't really do non-blocking in Ruby because there was to be non-blocking, you have to have something that is doing this like event loop thing and suspending and resuming things, but managing the actual like communication from the network usually, and then managing the calls to user code. And you have to have threads to do that. And I think when Python added their async stuff, they essentially implemented that like event loopy thing for you.
There's a default event loop, and you can write your own event loop or plug your own event loop in. But it's it's relatively easy to understand. It's just going around checking things and running things. Well, I think it's got some randomization in there so that it doesn't bias it towards some tasks. But it's the model is, I think, easier to understand. Although I had Luciano explain it to me, so I have an advantage there. Because there were questions like, wait a minute, how do you know when something has happened? And eventually it gets down to the operating system level. So it ties this thing in with the operating system, and it says yes, and it flips a bit, and then your event loop sees the bit. But I didn't have that full thing before I was able to. It's really nice to have somebody you can just ask endless questions and has all the answers. Because he's worked it all out.
Yeah, I mean, ultimately you have to have that like OS level event loop. You have to get there.
But people don't always say that. So you don't, when somebody's trying to build their mental model, there's this question mark.
I don't know how Python does it, but it certainly gets a little tricky when you get into, all right, so imagine that you have, you've got your event loop, and it's like calling all these things, and you probably have some very limited thread pool for the user code. Let's say your thread pool for the user code that's actually like executing in response to these events, let's say it's 10 threads. And so that allows you to do 10 things concurrently. But what happens if all of a sudden your all of those thread pool slots are all blocked, and your event loop then can't do anything else? It can't process any other user code. And so what
it's just waiting, it's just checking
it's just like, hey, are all you done yet?
Nope.
Are there any slots? And all 10 are full. And so then it just is building up a buffer of things that is ready to send on to the user code and execute the user code, but it can't. And so what typically is recommended in the JVM space for this is that things that to be blocking or take a long time, you actually allocate a fixed thread pool to. You actually delineate and say, these are my blocking operations, give these things a special thread pool, and then you leave your non-blocking stuff on the like very small thread pool, because that those slots are going to open up quickly because they're non-blocking, and so you're going to be able to like reschedule things onto those slots. And so then you have to, as a programmer, delineate, these are the blocking things, or when I say blocking, it could actually be non-blocking, but just take a long time, doing some heavy processing or something like that. So you have to delineate as the developer. These are the things for that thread pool. These are the things for this thread pool, for the non-blocking thread pool. And it just is...
it's hard to do concurrency without this kind of leaky abstraction thing, because it's like, oh, well, we have all these different strategies. Which one do you choose? Well, it depends on the problem you're trying to solve. It. You could try this one, it might not work that well, and then you try another one. It's like one of the nice things about Go is that it has this pretty basic model.
It gives you one way to do it.
It gives you, well, I think it's not, don't they also have some other...
I think you just get channels. And that's...
Yeah, communicating sequential processes, which is really... nice, but I thought you could do like actors and things.
I haven't seen actors on Go, but
what am I thinking? Oh, well, I don't know, maybe not. But not having to go, oh, now I have a whole nother problem to solve, which is figuring out how to, and the whole point of all of this is, as you say, optimizing performance. And so it's all about which ones which knobs you twist and which strategies you choose.
And it depends heavily on what you're doing, how you're doing it, and all those kinds of things. So another aspect to this is around CPU caches. So when you're doing multi-threaded stuff, one of the reasons why you want to have a small number of thread pools is one, because the context switching with threads is pretty heavy, and two, the better you can keep your CPU caches in line with what you're doing, the faster things are going to run. And so one of the strategies that some so like Play Framework, I remember, implemented thread trampolines or something like this.
I remember.
And this was the ability for when your async thing resumes, wouldn't it be really nice if you could resume it on the same thread
so you don't
as
have the
you were on before?
Switch.
So you don't have the context switch, and hopefully you have the CPU cache. Like hopefully that thread is being scheduled on the same CPU because you have a small number of threads. And so, yeah, one of those things where, man, it turns out to be a really complicated problem. And one of the annoying things is that it takes the developer having to figure out which strategy do I use where, and that depends heavily on what you're trying to do,
the context you're working in,
the performance that you need, and
yeah. So I try to scare people away from using any kind of concurrency. Just like the only reason for it is for performance. And if your performance is okay, don't mess with it. Don't go asking for trouble. It's like, if your performance isn't okay, well, look at the different approaches you can take. Maybe you can do something using a different architecture with different language or whatever. to solve that problem. But gosh, because wading into concurrency is like, oh, you thought you had this problem, and this is the joke that people have about regular expressions. It's like, now you have, well, now you have not two problems, you have dozens of problems.
Yeah.
And it's like, wow. And is there any way for us to make this simpler? I don't know.
Yeah.
I think it's going to take people smarter than you or me to figure that out.
Yeah. I mean, the good thing is that the ecosystems are generally defaulting now to non-blocking.
Yeah.
Which is usually a good choice.
Oh, sure.
Not always. So not right. Reactive is actually slower than non-reactive. So
because of context switch, or
all sorts of reasons, but you can imagine. All right, if I know that I'm going to have this giant stream of bytes coming in, it's a whole lot more efficient just to keep something allocated and just constantly read those bytes, versus going through this event loop and constantly checking, are you done yet? Do you have more to send me? Are you done yet? Is your buffer full? So the event loop actually has overhead to it that makes it, on the throughput perspective, actually slower. Mm-hmm. But usually if you take a system as a whole that's processing many things in parallel, getting
the net result is faster.
The net result is often significantly faster.
I mean, that's so weird because just on the top level, it's counterintuitive.
Yeah.
But then, you have to look at the entire system. And
it's like, are you optimizing for like single thing stream, or are you optimizing for many things at once? And most of our applications today should optimize for many things at once, not single stream processing. And so reactive it's gaining a lot more traction because Spring Framework uses it. You don't have to use it in Spring Framework, but they've made it a lot easier to be reactive. And a lot of the Spring folks have been trying to educate that developer group on reactive. But there's still a lot of confusion because of async and because it's harder. So I just had a question from somebody who is saying, all right, I need to call, a web request is going to come in. It's going to call this thing that is async. And I've got a problem because that thing that it's calling, it's going to respond at some point. And in their architecture, they had already returned the HTTP response before that async thing had come back.
So it's like a future or something?
Yeah, but but this is certainly something you don't want to do. Is your architectural pattern in reactive should be, no, don't return the HTTP response until that thing that you have spawned, until it is responded, mm-hmm. and then return the HTTP response, because then you get a full chain of a full reactive chain. Whereas I think there was a model pre-reactive where you would say, go off and do this thing, and you would return your HTTP response, and at that point you're not reactive. And it's so it takes a bit of a mind shift to be like, okay, how can this thing be non-blocking reactive the entire chain from start to finish? And then you have to deal with the programming model and all the async stuff associated with that.
So I also thought that part of reactive was some sort of what do they call it? Back pressure or flow, or that's a thing.
So that's in the reactive streams part of things, and back pressure is an important part of reactive I/O, non-blocking I/O, and it's also a important part of usually like actor systems. They need some way to be like tell for the consumer of some stream to say, like, hey, I'm backed up, like I'm full. I can't process anymore.
Stop putting new
things into the input. And so to be able for the consumer to communicate that up to the producer, and back pressure really, it's hard because with back pressure, let's say that your consumer can't keep up, but the producer needs to keep producing. And so what does it do?
It's like a video or audio stream or something. It can't just go, okay, I'll tell everybody to stop talking.
Right. Yeah, exactly. Right. And so there's places where you can back pressure all the way through the system. Mm-hmm. And that's really nice if you can do that. But there are other places where you can't do that. And so then you have to decide what your strategy is. Do you buffer? How long do you buffer for? What does your buffer do if it gets full? Does it start dropping? What does it start dropping? And so Akka Streams makes this very explicit in terms of back pressure, because when you're using Akka Streams, you have to tell it what behavior you want when back pressure happens. And so it at least puts that into the developer's hands, instead of just what we did before back pressure was kind of a thing, was buffers would just fill up and then things would crash, basically, is what would happen.
Yeah, but that doesn't happen usually.
That's right.
So it should be fine.
Yeah. And so an interesting example of this is like an IoT device that's sending sensor data. Mm-hmm. This is a simple use case where, you've got all these IoT devices, they're sending all this sensor data, and with a back pressure system, you've got some consumers that are taking that sensor data and need to consume it. Well, if those consumers can't keep up with that stream of IoT data, the ideal situation is that they could actually communicate that back pressure all the way back to the IoT devices and say, hey, like let off, instead of sending these telemetry things every second, why don't you send them every 10 seconds for a while until I can keep up?
And you can actually control those devices to tell them to slow down.
Yeah. But more often than not, what you do is you put a big buffering device in between those things, Kafka or whatever, and your Kafka system decouples the consumers from the actual stream of data. And so then Kafka just becomes this giant buffer. And
what happens when the Kafka buffer overflows?
Kafka has a bunch of different strategies for dealing with this.
So you could say, okay, depends on how if this is too full, now go pick out every 10th second one and throw away the other 9.
Yep. Yeah. So you can do log compaction. Mm-hmm. With Kafka, you can do like max size of a topic. So you can say, all right, this topic can only be 10 gigs in size, and it'll start rolling messages off the back, just forgetting the messages that are the oldest. So all sorts of different strategies for how you deal with that.
I think one of the big insights that I've been struggling with concurrency ever since I was in graduate school. And I think one of the big insights that I had was, first of all, it's about efficiency. And the second is that it's just a big pile of strategies.
Yeah.
And you have to, and there isn't a nice, simple guideline, because my brain always wants this, give me the formula.
Yeah.
I want to put this in and you tell me what to do. Nope. Yeah. It's not like that. And it's like understanding that is very liberating, because you go, oh, I'm not ridiculous for not understanding, but being able to just pull the right one out, because there isn't a right one. There's even within one system, several strategies might give you what you need.
Yeah. Yeah. And I think one of the challenges that we have today that causes some of this is that you as the developer have to decide what is your amount of time that you consider something to be blocking.
What problem are you solving?
Yeah. Like every time you do an operation on the CPU, it's essentially blocking. Should you make those every single operation async? No. So if an operation happens in under 10 nanoseconds, is it, do you leave that as blocking?
Depends.
But then
depends on your system.
But then if it takes 20 nanoseconds, should you wrap it in async and
be
non-blocking? Maybe. Yeah. So
what are you trying to do?
Oh, and then the streams one is interesting too, because how big is this list? Is it infinite? Is it is it fixed? If it's fixed size, how big is the fixed size? Are we talking 1,000,000 records, 1,000,000,000 records, 10 records? And so you as the developer have to say, all right, well, I think that the size is going to be this, or I think the amount of time that it's going to take is this. And so here's the strategy that I think works well with that.
And then you're running into the issue of premature optimization.
Right.
And it's like, and this is where I love the maxim, do the simplest, try, not do. Try the simplest thing that could possibly work. It's a variation of Occam's razor, which people get wrong. Occam's razor, you'll see it in movies. In Occam's razor, people go, "Oh, it's Occam's razor." It says the simplest solution is the correct one. No, that's not what Occam said at all. It's much more basic than that. It's just try the simplest solution first.
Yeah.
Because if you think about it, it's like, that's just a logical strategy. Why would you try the hardest one first? That's going to take way more time, and it still might not work.
Yeah.
If you try the simplest one and it works, you're done.
Yep.
So it's as dumb as that. And yet, and I think that's the case with programming. It's like, and I kept running into this in Python because I had come up from assembly language and all that. And so I knew how all the little wheels and gears meshed. And one of the first things I had to do was write a floating point math library in assembly language for some
fun
processor. It was actually, I don't remember anything about it, but and then I do something in a higher level language and I go, oh, well, I know about this, so I will optimize. It doesn't make any difference. And it took me a long time before I realized that, oh, in Python, it's probably already optimized. So don't get clever because you think you know something about this problem. And that's the same thing with any kind of concurrency. It's like, don't do it unless your program isn't running fast enough. And then even then before you get to concurrency, there's other approaches that you can take. So
and for me, coroutines is just the simplest thing that is a nice place to start. And I like that Kotlin has just built that in and made that basically the default. And coroutines work great with Spring Boot and other frameworks. So I can be non-blocking all the way down with coroutines, and it's an easy programming model, and likely it's going to be sufficient performance.
And so you've been using Kotlin coroutines? Yeah, because we decided for various reasons it was too advanced to put into the book.
Oh yeah, the coroutines they make async so easy. Mm-hmm. And because I want to be reactive and non-blocking in the applications I build, then I'm using coroutines. What's interesting is that oftentimes, like if I'm in Spring Boot, I'm actually adapting from their reactive API, which is not coroutines because it's not even Kotlin, it's Java underneath the covers. I have to adapt from that reactive API to coroutines, but the coroutines library has made that super easy. They have all these adapters where you get like one of these reactor things back when you make a non-blocking call, and then you call like, I don't know if it's .await or something like that, different terminology depending on the library. But you call some extension method on that thing that turns it into a coroutine for you. And so they've done all the hard work of adapting these different reactive APIs to coroutines. And so it feels pretty natural and pretty good, even though they're not actually based on coroutines under the covers, but they're still non-blocking.
This is one of the things that I've found really nice in Kotlin is the thought given to the programmer experience. It just seems so clear in virtually everything in the language. It's like, we want the programmer experience to be as nice as possible. And we're not, because I feel like Java did like a lot of compromises for got to get the thing out. We're going to be the default language across the internet, and we're in a hurry to just slop a lot of these things in. Serialization. We'll fix that later. Lots and lots of things that are getting fixed later, but only somewhat fixed.
Yeah.
It's just, at some point, I think we need to move away from that language.
Yeah. Yeah. I mean, I don't really write any Java anymore.
No. Why would you?
Yeah. But I can easily be reactive in Kotlin and appreciate that experience. It's pretty nice. And hopefully that'll be a gateway to helping other people be reactive on the JVM. I learned it and did it first in Scala and had to learn monads. And now I love them, of course, but Kotlin coroutines are so much more approachable for dealing with async. On the database front, there's actually a couple of new database libraries that are non-blocking, and I've been using some of them and had pretty good experiences with them. So that's been nice to see. There's one called R2DBC, which is, I don't know, reactive JDBC, and that one's interesting. And then there's another one called async, which is written in Kotlin and native database drivers that are reactive. In production, I've used a Scala one, which was, it has all these disclaimers like don't use this in production, but it was one of the first actual relational database reactive drivers, and it worked great in production. So yeah, I think reactive is certainly here. People have been saying that reactive kind of maybe goes away when we get Loom, because then we've got fibers, but I think still it's going to be reactive. Like there's no reason to waste those threads. So our underlying libraries are going to be non-blocking, but maybe the programming model for Java developers gets a lot easier. And then I know like Kotlin and Scala will be able to leverage those and probably be more efficient or something.
And do you know, is Loom going to be part of Java 17?
I don't know what the time frame on that is.
I haven't looked at it, so
yeah.
I mean, it seems like since that's the next long-term support version, we would hope.
Yeah.
But it's all.
Yeah. So at the end of the day, it is hard to go reactive, but people should, and it's a good default. It's a good default. It's a good place to try first
for speed ups. If you need to speed your program up, that's a good default.
If you're writing anything that is multiple user, like if you're writing a CLI, there's only ever going to be a single user at a time of that program. Like you don't need to be reactive. But if you're writing a service that's going to have concurrent requests, then reactive is a really good default.
Okay. Yeah, I mean, see, there's a nice bit of lore. It's like, because we say, there's all these strategies for speeding things up, but if you know which ones you should try first, that's very helpful.
Yeah,
because you go, try this one. It's easier. If it works, you're done. If it doesn't, then you have to look for another strategy.
Yeah, and I will say, caveat to that is if you don't have anything to be non-blocking on, then there's no reason to be reactive and non-blocking. Like if you're if what you're doing is just like full CPU intense, like if you don't have anything to non-block on, like
there's no boundaries. You're not crossing any of these boundaries.
Then there's reactive is going to give you zero.
Well, it'll actually cost
because the programming model is more complex.
Yeah. Well, not only that, but you're doing context switch
and the context switch.
Yeah, so it'll actually slow you down.
Yeah.
You keep mentioning Spring Boot, and I know there's Spring.
Yeah.
What's the difference between Spring and Spring Boot?
Spring Boot is just like the developer experience kind of nice layer on top of Spring Framework. So Spring Framework is the traditional dependency injection thing, and then Spring Boot is just some nice out of the box easy ways to use Spring Framework.
It's like pre-configured setups for different problems that you might want to solve. Okay.
Yeah.
So it's still basically Spring.
It's Spring underneath the covers, but yeah, with some nice layers on top.
And the core idea of Spring is dependency injection?
Yes.
Okay. I think we should sometime delve into dependency injection because it's like I sort of see what's going on there, but it's not intuitive to me.
Yeah.
And then there are some people, I mean, I think I've read or seen some things where they're going, oh, this dependency injection thing is not...
Bump kiss? Yes. Dependency injection is bump kiss.
Or bupkis?
Bupkis? What's the word there?
I don't know. Anyways,
is that topic for another? Okay. Yes, that is my perspective, and we'll do that.
Well, then that makes it even better.
Yeah, I'm not a fan of dependency injection.
Cool. I feel like that kind of thing gives you a better insight rather than somebody going, dependency injection is awesome. Then I don't know, the trade-offs. Yeah. But if you're already thinking that it's...
I do a lot of dependency injection. So
but you don't like it.
It's not purely functional.
Okay. Yeah. Okay.
Yeah. We'll save that for another episode. But
save that for another episode.
That'll be a good one.
Okay.
Cool. Well, that was fun.
Yeah.